So LeetCode number 416, partition equals subset sum. So for this problem, you're given an array of numbers and you need to return true if you can partition those numbers so that the sum of the two partitions are equal. So for example, here you can take the 1, the 5, and these other 5, and they sum up to 11, which is the sum of the other partition. So basically you can take or not take some numbers and their sum needs to be equal. So this problem actually gets accepted even if you do a brute force, at least in JavaScript. So if you just take like all of the possible sums that you can make and you check if there are two equal, it does actually work, or at least I got it accepted once. However, the dynamic programming solution, I'm going to explain to you the dynamic programming solution with a technique that I've learned yesterday from a friend of mine, and we're going to call that technique to take or not to take. So we're just going to lay down the framework of the problem, just like a usual recursion solution, and then I'm going to show you the take or not to take technique. So the first thing is, since you want to have two partitions that sum up to the same value, you want to check the sum of the whole array, which obviously takes O of n, and then if that sum is odd, so if it has a remainder with 2, then you definitely cannot partition it into two equal sum partitions, because obviously then it would have to be even. So we just check if it is odd, and if it is, we return false straight away. So this is just part of the problem, right? And now your target is sum divided by 2. So if you find any subset of these numbers that has a total sum of target, then you can return true, right? Okay. And now, since we're going to do a dynamic programming solution, I'm going to need a cache, which is just a matrix. It's just that in JavaScript, it's a bit long to make a new matrix. And now we're going to have to use a recursive function. I call that solve. Some people call it DP. You can call that whatever you want. But essentially, you have a function that searches through all of the possible states, all of the possible combinations of parameters. So you have like a search space, which is basically a matrix, and you want to navigate to that search space and find the solution, if there is a solution. Okay, so our recursive function is going to check, and this is where the technique comes in, is going to check what is the solution if we take the item, the number at index I. We're going to call this index I, right? So we check what is the solution, is like, can we have a solution if we take the current item? And then we're also going to check if we can have a solution if we do not take this item, right? Okay, so also you want to keep track of your current sum. So for example, you could be coming from, like, let's say at the beginning, obviously your sum is 0 because you haven't taken any numbers yet. But then, for example, I could get to this 11, like when I is 0, 1, 2, when I is 2, I could have came from picking these two elements, and so now the sum would be 6. Or I could have come from not picking these two elements, and so the sum here would be 0. So you see why that is a parameter also, because it changes the way you're navigating the search space. Okay, so what you do now is you have your usual base cases, and you have your check to see if the arguments are in the cache already. So if I is out of the bounds of the nums array, you return false, obviously. Then if the sum is above the target, you return false because all of the numbers are positive. So you cannot like move backwards in the sum. So yeah, you just return false as soon as you are greater than the target, because there are no negative numbers. And then if the sum is equal to the target, you return true, because that's what the problem is asking for, right? Okay, and now is just the dynamic programming part. So this is where you check if you already have your result in the cache. So if the cache for those parameters, for those input is not undefined, then you just return that cache. Otherwise, now comes the actual part where we need to compute the result. So the result, like we're searching, can we solve the problem if we take or not take I? So yeah, we just do those two choices. So you update your cache with the result, which is, can I solve this if I not take this element? Or can I solve it if I do take this element? So you see I'm adding to the sum the current element, meaning that I'm taking it into the partition. And I'm also doing the same thing, but not adding it to the sum. So I'm just taking the original sum without adding it. And that gives me the solution, the possible solution eventually maybe, if I do not take the current number. And in any case, I move forward with my I pointer, right? So this is the technique. Sometimes you need to do a max, sometimes you need to do a min. In this case, you had to do an OR, because if either one of these two returns true, then you can indeed solve the original problem, right? Like, it doesn't matter if this one returns true or if this one returns true. All you care about is one of these two is returning true, right? And yeah, that's it. Now you've updated your cache. Now you just want to return that and you're done. So yeah, I'm going to submit the solution to show you that it works. And you can see why the memoization here is useful, because if you just did all of the possible subsets in your nums array, you would have 2 to the n possible subsets. So the time complexity would be that, 2 to the n, where n is the amount of numbers that you have. And you can see why the memoization is useful, because here you only have 2 parameters, and this can go from 0 to n, and this can go from 0 to target. So you basically have a solution that is calculating at most, is doing this solve function at most n times target times, right? So yeah, that's how you can see that the memoization is actually saving you time. So that's it from me today. Hopefully this has been useful to you as well. Thank you and bye.